When the ground beneath a building suddenly shifts, most people imagine concrete cracking, windows exploding, and thousands of tons of steel being thrown violently from side to side. But in Japan, some skyscrapers can sway for minutes without collapsing. And here's the strange part. That movement isn't necessarily a sign that the building is failing. It's part of the plan. Japan sits along the Pacific Ring of Fire, where several tectonic plates collide beneath the country. Earthquakes aren't an unusual disaster there. They're a reality engineers have spent generations preparing for. So Japanese architects and engineers had to answer a terrifying question. How do you build a city where the ground itself can suddenly turn against you? The answer wasn't to build buildings that were simply stronger. They learned to build them smarter. And some of the technology they developed can make a building behave almost like a person bending their knees during a punch, absorbing the force instead of trying to stand completely rigid. But there's a catch. Making a building survive an earthquake isn't about stopping it from moving. It's about controlling how it moves. 1. The building that refuses to fight the earth. Imagine standing on a train while it suddenly accelerates. Your first instinct is to stay completely still. But your body naturally bends, shifts, and adjusts to keep you upright. A building can do something surprisingly similar. When an earthquake strikes, the ground doesn't simply move up and down. It can suddenly push, pull, and shake sideways, sending enormous forces through the structure. And here's where conventional thinking becomes a problem. A rigid building tries to resist that movement. But the more violently the ground moves, the more force can be transferred into the building. So what if you stop trying to fight every movement? Japanese engineers developed systems that allow buildings to absorb and redirect some of that energy. One of the most important examples is base isolation. Instead of planting the entire building directly onto the ground, engineers can place special isolation devices between the building and its foundation. Think of them as giant shock absorbers. When the ground moves suddenly, the foundation can move with it while the building above moves much less. It's almost like putting a heavy object on a cushion and then violently shaking the surface underneath it. The surface moves. The object doesn't have to move nearly as much. But that raises another question. What happens when the earthquake is so powerful that even isolation isn't enough? That's where Japanese engineering gets even more interesting. Because some buildings don't just isolate themselves from the earthquake. They actively fight back against the movement. 2. The giant shock absorbers hidden inside buildings. Inside some modern buildings are devices called dampers. Their job is simple. Take the energy from the building's movement and turn it into something less dangerous. When an earthquake causes a building to sway, the dampers resist that movement. Instead of allowing the building to keep swinging violently, they help reduce the motion. And this matters because a skyscraper isn't just a giant pile of concrete. It's more like a gigantic flexible structure. If you push the top of a tall building, it wouldn't necessarily snap. It could bend and sway. That's actually useful. Because if the structure is designed correctly, controlled flexibility can prevent the earthquake's energy from being concentrated in one catastrophic location. But there's an even bigger problem. What happens when the earthquake doesn't stop after a few seconds? Because that's when things get really dangerous. 3. The earthquake doesn't have to destroy the building to hurt people. A building can remain standing and still suffer enormous damage. Furniture can fall. Glass can shatter. Ceilings can collapse. Pipes can rupture. Electrical systems can fail. And people can be injured long before the main structure actually collapses. So Japanese earthquake engineering isn't only about answering, will the building still be standing? It's also about what happens to everything inside it. This is why earthquake-resistant design involves much more than steel and concrete. Engineers have to think about elevators, windows, plumbing, interior walls, emergency systems, and even the objects people keep inside their homes. Because surviving the earthquake is only the first battle. The next battle begins after the shaking stops. And that's where Japan's approach becomes particularly interesting. 4. The secret isn't just the building, it's what happens around it. Imagine two buildings experiencing the exact same earthquake. One survives because its structure was designed to absorb the movement. The other survives structurally too, but its surrounding infrastructure fails. The roads are blocked. Water lines rupture. Power disappears. Emergency vehicles can't reach the building. Suddenly, structural survival isn't enough. Japan therefore treats earthquake preparedness as something much larger than individual buildings. It involves roads, bridges, evacuation areas, emergency communication systems, fire prevention, and disaster planning. Because engineers eventually learned an uncomfortable lesson. You can't protect a city by making only its buildings stronger. You have to make the entire system more resilient. And that brings us to one of the most fascinating questions in earthquake engineering. 6. The ground beneath the building can decide its fate. Two buildings can experience the same earthquake and suffer completely different levels of damage. Why? Because the ground underneath them isn't necessarily the same. Some areas have hard rock beneath the surface. Others have layers of soft soil. And during an earthquake, that difference can become extremely important. Soft soil can amplify shaking, causing the movement at the surface to become much stronger than it was deeper underground. Imagine shaking a bowl of jelly compared with shaking a solid block of wood. The movement behaves very differently. So before engineers even think about designing the building, they need to understand what the building is sitting on. And this is where earthquake-resistant construction becomes less like simply building a house, and more like solving a puzzle. The foundation, soil, structure, and expected earthquake all have to work together. But even if engineers get all of that right, there's still another enemy: the building itself. 7. Why engineers sometimes want buildings to bend. Here's something that sounds completely backwards. A building that bends can sometimes be safer than one that refuses to bend. Think about a tree during a hurricane. A perfectly rigid tree might snap under the force. A flexible tree can bend with the wind and return to its original position. Tall buildings can use a similar principle. Instead of designing a skyscraper to remain completely rigid, engineers can design its structural system to deform in a controlled way. That allows the building to absorb some of the earthquake's energy without experiencing catastrophic failure. But controlled movement is incredibly difficult. Move too little, and enormous forces can build up. Move too much, and the building can suffer severe damage. So engineers are essentially trying to find the sweet spot between rigidity and flexibility.